So if we have this, we have 2 moles of gas on the reactant side and 4 moles of gas on the product side. And so to make it high pressure, you just decrease the volume. If you decrease the volume, you're going to favor which side? The side with fewer moles of gas, the side that takes up less space. And so you would look for which side requires less space. And so normally that's the way I think about it if I'm dealing with pressure. Sometimes it's easier to think in terms of that because under standard conditions, everything has the same pressure. There's different ways to increase the pressure. You know, we could increase the pressure by adding an inert gas. So let's say I'm just interested in the total pressure. If I add inert gas to this, like nitrogen, is that going to have any impact on this equilibrium? So if I increase the pressure, the total pressure, by adding nitrogen doesn't even participate in this equilibrium, and so it's not going to have any impact. But if I increase the pressure of everything by like crunching it down or injecting more gas in there, then that will change. Injecting more of these gases in there, then that will change things. So that's what we have. Does that answer the question? Okay. Were there any other questions? Number 23. Okay. Equal. Oh, go ahead. Yeah, if you have 2 unknowns, but the 2 unknowns are related by another equation. The other equation is stoichiometry. We have to have it in a certain ratio. And so actually we'll have 2 unknowns and 2 equations in which we can solve it. Or the other thing, there are other scenarios here. This happens in often in more advanced classes. In more advanced classes, you might go, oh, there's not enough information to solve the problem. And that's true. There's not enough information to solve the problem for a single specific answer, but there is enough information to solve it to an equation. So what you can do is you can generate an equation and say, well, at this limit, we'll have this answer. At the opposite limit, we'll have another answer. So normally what we do is if there are 2 variables and you only have 1 equation, then we'll solve it to an equation, and then we'll think, okay, at the limit of this x value, what are we going to get for y? And at the opposite limit of that x value, what are we going to get for y? And then you answer with a range. You'd say the range for this we would expect is from here, y value from here to here. And so we often do that, and then you have to put in some what you call you'd have to know something about the limits of x. You know, it can't go from minus infinity to plus infinity, you know, and that's often the case. It doesn't, and so we can limit it. In this particular problem, you just get a ratio, so you're going to get the ratio. I know they ask for the reactant to product ratio, but it's a product to reactant ratio. We can get, you know, products over the reactants and then solve that. And so that ratio, whatever that ratio is, has to equal this constant value. And so we can see how it varies. So for example, if the SO2 goes up, the SO3 does this. And so that's a case where we aren't solving it for one specific answer, just solving it for an equation. And that's often done, but it's not done at lower division classes because it makes people uncertain about that. Okay, were there any other questions? Yes. All right. I did post the key yesterday, but I noticed I had to correct some errors I made. So I fixed the key. It's posted on there. It should say corrected. Today I need to finish up the previous lab. You know, we had the calculations for that lab. I want to finish up the calculations. calculations for that. And then I need to talk about acid-base mixtures. We have lots of different types of acid-base mixtures. This is actually the beginning of chapter 17. One of the acid-base mixtures is a buffer, the weak acid plus the weak base that we did last week. Another acid-base mixture is a titration. In a titration, the buffer that we looked at last week, there was no driving force for reaction between the acid and the base, but typically in an acid-base titration, there is a driving force. We're going from stronger acid to weaker acid. And then we have a titration or neutralization reaction. So we're going to talk about titrations after that. And then I have this lab broken up into two parts. In the first part, we're going to just do a regular titration like you did in Chem 1A, using phenolphthalein. And then in the second part, we're going to do a pH titration. And so today we'll do just the regular titration. pH titration is much more work and much more time is involved there. So let's see. All right, so we were looking at sodium carbonate, I think. Is that right? I think that's where we left off. Is that correct? Or yeah, okay. Sodium ions are neutral. We don't worry about them. In Bronsted, they're not a proton donor. The only protons would be located in the nucleus, and those aren't going to be donated. In Lewis, these are too weak to be electron pair acceptors. Carbonate, however, is a Bronsted base. So we'll look at carbonate right now. It's a dibasic base. Did I write the steps? Step 1, step 2, step 3? Right? Yeah. Okay. And what we want to do is we want to do the stepwise. Did we already finish step 1? Can't remember. Or have we not started? We just started. Okay. Let's take a look at carbonate. The first step is when we do hydrolysis, we only do one step at a time. Now, carbonate's a weak acid, and so it will pluck off one of the protons here and form hydroxide. Bases hydrolyze water to form hydroxide. This is Kb1 for carbonate, which is equal to Kb for carbonate. But when I look in the book, carbonate's not there, so I need to look for the conjugate. And the conjugate acid is going to be bicarbonate. And so this is going to be Kw over the Ka for bicarbonate. Interestingly, although I'm not necessarily going to write this, this is also equal to Kw over Ka2 for carbonic acid. Carbonic acid is what we call diprotic acid. So there are different ways we can think of these types of things. But if we remove the first proton, that's Ka1 actually. The first proton for carbonic acid is Ka1, and therefore the second proton will be Ka2. And so this is why we call it Ka2. But we should be able to find the Ka value for bicarbonate. All right, so what was the initial concentration of carbonate? Yeah, 0.1 molar. And then the water, pure liquid. And then we assume that nothing's happened yet. So 0 and 0. This is going to be minus X molar. A weak acid, the K is not very large. If the K were listed as very large, like no number, just large or very large, then we would just hydrolyze all of it. This is going to be 0.1 minus X. This will be X molar. This will be X molar. First, let's take a look at the Kb. We want to start off with the largest K value. And I don't know if this is carbonate a better base than water. Actually, yeah, I would suspect it's a better base than water. But if it wasn't, then we'd start off with water, Kw. Well, anyway, Kw is 1.0 times 10 to the minus 14. Now we have to look up Ka for bicarbonate, or Ka2 for carbonic acid. So let's go to the chart here and take a look. I see it here. So Ka1 for carbonic acid is 4.4 times 10 to the minus 7. Ka2 for carbonic acid is 4.7 times 10 to the minus 11, which is equal to the Ka for bicarbonate. When I look at this value here, it's bigger than water. Water Kw is 10 to the minus 14, so this should produce more hydroxide, although water is more concentrated, so we don't necessarily know. We start with the biggest K. Now the biggest K will be, actually that's Ka. I'm trying to find Kb here, so I need to do an extra step. So this is going to be 4.7 times 10 to the minus 11. Put that down here, 4.7 times 10 to the minus 11, which is going to give me a Kb of, let's see, calculator. Let me know if you have it. 2.123. In this, we're allowed 2 sig figs, so we would round this to 2.1, but we don't have to round it yet because it's fine. Just carry extra digits. So this is actually a lot bigger than water. You know, the Kb for this is 10 to the minus 4. Means it's a moderate base, excuse me. So we're going to go ahead and solve this for X. X will be equal to the bicarbonate concentration at equilibrium times the hydroxide concentration at the equilibrium divided by the carbonate concentration at equilibrium. And so in other words, it's going to be equal to x squared over 0.1 minus x. Now, I'm worried about the simplifying assumption in this case, because when you look at the Kb, it's kind of on the bigger side of small. You know, it's 10 to the minus 4, it's still small, but I think it's probably going to fail. And so, but you know what? It's so easy to do. We're going to go ahead and do it because this is going to simplify it into x squared over 0.1. And so it's a quick calculation to calculate x. And if it fails, then that's all right. Can somebody calculate x? Is with those. Do you guys, do any of you watch the videos? No? Yeah. Is the audio okay or is it? Yeah. All right. All right. Okay, we were talking about this. Here we have the bicarbonate left, and we got to figure out what to do with the bicarbonate. And we look back. The solution is a base solution. It's a base solution because we started with carbonate, which is a base and only a base. Carbonate cannot be an acid, and therefore we only look for hydroxide contributors. Ka is both a hydroxide contributor, Kb, and a hydronium contributor, Ka. And we're only going to look at the Kb for bicarbonate. We're going to ignore the Ka. Ultimately, because we don't need to worry about the Ka. I'll show you shortly. However, if the solution were amphoteric, that is, it started off with bicarbonate, i.e. sodium bicarbonate, we have to do both Ka and Kb, not stepwise. We have to do it simultaneous. With Kw. So we have Ka, Kb, and Kw simultaneous. You tried the math on 2 equilibria, right? Simultaneous. And so you just have to step it up a notch to do 3 equilibria simultaneous. By the time you get to 3 equilibria simultaneous, it's probably best just to use a computer to solve it, not try to solve it by hand, maybe, unless it's a simple scenario. We will have some simple scenarios for the amphoteric. Okay, this is going to dictate what step 2 is. So we call this step 1 here. Step 2 is just going to be the Kb for bicarbonate if it's bigger than Kw. So we go to the next biggest K. Is it going to be Kb2 for carbonate or Kw? So let's figure out what our next step should be, because if Kw is bigger than Kb2, we'll do Kw next and then Kb2 at the end. If Kb2 is bigger, then we'll do that first before Kw. And so let's first calculate what Kb2 for carbonate is. Kb2 for carbonate is just equal to Kb for what? For bicarbonate, which is equal to Kw divided by Ka for what? For carbonic acid, which is Ka1 for carbonic acid. And so this is going to be 1.0 times 10 to the minus 14. This is going to be divided by the Ka for carbonic acid, or Ka1 for carbonic acid, which is going to be 4.4 times 10 to the minus 7. Plug that in here. 4.4 times 10 to the minus 7. Alright, so let's calculate this. I get 2.272 times 10 to the negative 8. Is that what you guys get? So what's bigger, Kb for bicarbonate or Kw for water? Kb. So Kb is bigger than Kw. So therefore, step 2 is not going to be Kw. Step 2 is going to be Kb. So we have bicarbonate plus water is going to form carbonic acid, the conjugate acid, plus hydroxide. So we're looking for hydroxide producers here. And we just calculate KB. This is to 2 sig figs, would be 2.3, but we're going to leave it 2.272. It's 10 to the minus 8. We aren't going to round things until the very end. Okay, now how much bicarbonate do we have? Do we have 0.1 molar bicarbonate? The answer is no, we don't have 0.1 molar bicarbonate. How much bicarbonate do we have? We have a lot less. The reason we have a lot less is because there's only 4.5% ionization here. We had 4.5% reaction or 4.5% ionization. It's a weak acid. You know, strong acids should have closer to 100% ionization. This is not really, I mean, this is a weak base, sorry. But bases, when I say ionization, this is actually incorrect because carbonate does not ionize. Do you see that? What ions does carbonate break up into? It doesn't break up into ions. It hydrolyzes water to form new ions. Do you see that? And so I really shouldn't say ionization. I really should say what? Yeah, I should say hydrolysis. So weak bases partially hydrolyze water, strong bases completely hydrolyze water. That's what we say. But this is only 4.5% hydrolysis. Well, bicarbonate's even weaker. And bicarbonate's going to have a lot less hydrolysis. But if this is 4.5, how much do we start with? Now, what we're going to do is we're going to carry this down. This is how much bicarbonate we formed in step 1, so we're going to drop this down to step 2. 0.045026.00. So 0.0045026 molar. And then we're going to assume that nothing's hydrolyzed yet. And so we should have 0 molar carbonic acid. But what about the hydroxide though? Didn't we make hydroxide in step 1? Yeah, we made hydroxide in step 1. And so what we're going to do is we're going to add to it in step 2. And so the bicarbonate has to be transferred down to step 2, and the hydroxide also has to go down to step 2. And so coming down here, we're going to have 0.0045026 molar. Now there's going to be a Le Chatelier type effect going on here. So if you already have a lot of product here, we don't need to make much to come up with a ratio. And so the amount of change is going to be even smaller than expected. So we expect an extremely small change because it's 10 to the minus 8. But that change is going to be even smaller. That it's going to be compounded by having some product here. So the change is much smaller than expected based on just K because we have the common product here. And so, but I don't know what the change is, so I'm going to call the change minus X molar, and then plus X molar, and then plus X molar. If both of these were 0 here, X would be bigger, but since we already have a lot of hydroxide here, X is going to be smaller. And so this is going to be 0.0045026 minus X molar. This is going to be X molar. This is going to be 0.0045026 plus X molar. Only reason I carry the extra digits is just to avoid round-off error. It's a bit of a hassle. So this is going to equal the carbonic acid concentration at equilibrium times the hydroxide concentration at equilibrium divided by the bicarbonate concentration at equilibrium. And this is just going to give us the X times 0.0045026 plus X divided by 0.0045026 minus x. All right, here I feel pretty good about the simplifying assumption because k is pretty small and I got product here to begin with, and so I would go ahead and use the simplifying assumption in this particular case. Well, I use it in all cases, so it just makes the math a lot easier. And then just check it. And so the binomial on the top, which is 0.0045026 plus x, is just going to simplify it to that, and the x is going to drop. The x drops out of the bottom one too, 45026. And so this makes the math very easy because it's just equal to x. So let's take a look at the percent change, which is going to be x over 45026. Times 100%. And so x is just the k, what we call the kb, or the k value, 2.272 times 10 to the minus 8. .272 times 10 to the minus 8 divided by, what is this? Why am I getting this? Somehow I got these pop-ups coming up. This browser. 0.0045026 times 100. .0.000504%. When you see a percent change this small, then there's no reason to use the quadratic. You know, you aren't going to get a better answer because the simplifying assumption is no problem. And so here, yeah, I wouldn't even bother solving the quadratic. And also, the quadratic would be kind of a time sink because of the math, rearranging this. And the thing is, I wouldn't expect a much better answer regardless. So here, what are we going to get? 0.0045026 plus this number. I wonder if I could put this in memory. Plus 0.0045026. This is going to give me 5.00719 over here. This one's going to be x, which is k, which is 2.272 times 10 minus 8. .272 times 10 to the minus 8 molar for the carbonic acid. And then the bicarbonate would be 0.0045026 minus 2.272 times 10 to the negative 8. Maybe I miscalculated the other one. Let me double check the other calculation. 0.0450257 molar. And so let me double check this last calculation over here. 0.0045026 plus 2.272 times 10 to the negative 8. Oh yeah, I did. I screwed up this calculation, sorry. This is going to be 4.50. Oh, actually, let me get it in decimal form so you can compare .0045026. 2. All right, let's double check our K value here. So the K value based on these concentrations times 2.272 times 10 to the negative 8 divided by 0.0045026 gives me 2.2720 times 10 to the negative 8, 0.1. So that looks good, right? That's right on, pretty much. And so we're good. But the problem is this. Will this screw up the previous K value? You see, the concentrations changed a little bit, right? The bicarbonate, I lost a little bit of that. And the hydroxide, I gained a little bit of that. Is that enough to perturb the previous equilibrium? Yes, it's going to perturb the previous equilibrium, but is it going to perturb it significantly? And so what I'm going to do is I'm going to go back and recalculate the previous K value using these new concentrations. So I have the bicarbonate, which I lost a little bit, and the hydroxide I gained a little bit. And so let's see if that's going to upset this. And so I'm going to go with the original, well, let's go with the, what are we doing here? Okay, I need the bicarbonate concentration. The new bicarbonate concentration is going to be 0.0045027. And the new hydroxide concentration is going to be, so times 0.0045062 divided by the carbonate concentration, which I have up here, which was 0.095494. If I did the math correctly on that one, I probably should check that. And with the new values, I get a K value of 2.12292. It didn't change the K value at all. Before it was 2.12292. Now it's 2.12292. Do you see that? So these new concentrations do not perturb step 1. In fact, it was a negligible change, we say, here. And so this was a negligible change. That change was 0.0005%. Hydrolysis in the second step. And the same thing over here is a triple. Both of these are negligible changes. Therefore, step 1 is not perturbed. And we are justified in using the stepwise. Method instead of the simultaneous method. All right, we only have 1K left, and that 1K will be KW, so that's our step 3. How much additional hydroxide are we going to get from KW? And so we're going to go with H2O liquid plus H2O liquid. This is going to produce hydronium and hydroxide. Initially, we're going to assume that nothing's happened yet. And we haven't generated any hydronium, so there would be 0 molar hydronium. However, the hydroxide is not going to be 0 molar. The hydroxide is going to be from the previous step. It's going to be 0.0045026.2. I'm carrying way more digits than needed, but I'll just go ahead and do that. And so this is going to go down to step 2. Or not step 2, we're on step 3, sorry. Normally, if both of these were 0, we'd make 10 to the minus 7 and 10 to the minus 7 molar. But now we have a bunch of hydroxide in here, and so the change is going to be quite small. So this is going to be plus X molar, and then plus X molar. And so we're going to end up with X molar here, and then 0.0045026.2 plus X. You can read that, sorry. I'm going to go with narrow pen. This is Kw. Kw is equal to the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. And so the hydronium is just X. The hydroxide is 0.0045026.2 plus X. Now the same thing here. We're going to have a lot of product here, so the change is going to be even smaller than expected. And so there are 2 reasons why this change should be very small. One is Kw. You know, Kw is 1.0 times 10 to the minus 14. The change is going to be small in the forward direction. 2, we already have a product here, so that's kind of Le Chatelier's before, Le Chatelier's. So it's going to try to push things to the left. It's got to go to the right because we have 0 here. And so I'm going to go ahead and use the simplifying assumption, 0.0045026.2. And that makes X, calculating that, quite easy. And so X is just 1 times 10 to the negative 14 divided by 0.0045026.2. And that gives us 2.22 times 10 to the negative 12. Now let's calculate the percent change since we use the SA for this. The SA in this step here. The percent change is 2.22 times 10 to the negative 12 divided by the initial, which is 0.0045026.2 times 100. And it's going to be 0.70, so 1, 2, 3, 4, 5, 6, 7, and then a 4, 9. I'll just leave it. I ran out of room, so about 5 times 10 to the minus 8% change. So there's no reason to use the quadratic here too. We get the same answer. So let's double check. Well, let's go ahead and calculate the concentrations here. And so the hydronium concentration is going to be 2.22 times 10 to the minus 12 molar. It's very small. And then the hydroxide, is 10 to the minus 12 going to have any impact on this? No, I didn't carry it enough. I'd have to carry, let's see, how many decimal places did I carry? 3, 6, 9, 10. I carried 10 decimal places. It's not enough. We're not even going to see it till 12. So it's just going to come out the same, 0.0450262. It's good it doesn't change it because did we perturb the previous step? No. I mean, it was a negligible change here, so it didn't perturb. And so, so we're good. Stepwise is okay here. So all 3 steps led to a cumulative total of this much hydroxide. Well, that much hydroxide gives us a POH of what? And so we can calculate our pOH, which would be equal to the negative log of the hydroxide ion concentration total. Now the total hydroxide is the sum of the 3 steps, right? This is the combined hydroxide. That is, in other words, this is equal to the negative log of the hydroxide from step 1 plus the hydroxide from step 2. Now this is the additional hydroxide from step 2. So the hydroxide generated in step 2, which is the X, value here, plus the hydroxide from step 3. Again, this is the X value. This is not the, I'm not going to add like 0.045 plus, 0.0045 plus 0.0045, there. It's just the X's, the changes. And that came out to this. So what is the pOH? Let's go ahead and calculate that. This is going to be the negative log of 0.0045062. Which gives me a 2 point. Now this is 2 sig figs in the concentration. I should be allowed 2 sig figs, although I'm not keeping track of decimal places so strictly. But this is going to give me 2.346. So I'll carry 1 extra digit. This is 3 sig figs here because everything after the decimal is significant. And this is going to give me a pH. Okay. 14 from that is going to give me 11.653. So to 2 sig figs, the pH is 11.65. pH. Now, if this question only asks for pH, was it really worth doing 3 steps? If this question only asked for pH, could we have gotten by with just step 1? Yeah, if we calculate the pH after step 1, let's take a look at here, which is the negative log of 0.0045026 minus 14 from that, 11.653. So if we stopped at step 1, we would have gotten a pH of 11.653. Does it make any difference? No, because step 2, K2 and K3, K2 would be for step 2 and K3 would be for step 3, are small. And those weren't expected to contribute much. So for most acids, unless the step 2 Ka or Kb is significant, and what do I mean by significant? I should be a little bit more specific. Let me redo this here. Let's say if it's greater than or equal to 10 to the minus 2. If it's 10 to the minus 3, we probably can ignore it without causing too much damage in the pH. All right. But if we want solution inventory, then we have to do all 3 steps. Actually, let's put that here. Let's just say, if we're doing solution inventory, all steps are required. If we're doing pH, then maybe step 1, possibly step 2. I mean, you could do step 2 and see if it contributes, but for sure step 3 is not really going to contribute much. And if it did contribute significantly, we're doing it wrong. You know, we need to do this simultaneous. All right, so if you have a beaker that's labeled 0.1 molar sodium carbonate, what's in it? Let's start off with the species that's going to be the highest concentration. And this one I'm just going to do in my head, and that is sodium ion concentration. What's the molarity of the sodium ion concentration? I could do an equation for this, but it's going to come out to 0.2 molar. All right, what species is going to have the highest concentration after sodium ion? So we go back up here and take a look. And it looks like carbonate. This is the end of the line for carbonate. And so it doesn't change after step 1. So this is going to be 0.095 molar. If we round this, then it rounds to 0.1, but I don't want to round this. Although we're only allowed 1 sig fig, you know, I'm going to leave it at 0.095 molar. Okay, and then we go to bicarbonate. This is not the end of the line for bicarbonate. Bicarbonate goes down to step 2, and then it stops here. And so bicarbonate has this molarity, which we'll just do 0.0045, just slightly under that. 0.0045. Okay, then what? Then it's either carbonic acid or hydroxide. It looks like hydroxide is it, but hydroxide goes down to step 3, and then we have it here, 0.0045. Actually, these are out of order. We should have more hydroxide than bicarbonate. We should switch those here. In terms of ranking, hydroxide is going to have more, even though their concentrations look to be the same. And then what? Then it looks like carbonic acid. Which is going to be 2.2. We'll just call it 2.3 times 10 to the minus 8. I'm going to put it in decimal form. I'll go with 7 zeros, and then a 2, 3. Yeah, 2, 3. Round 2. And then there's one more species left. What is it? Hydronium. All solutions contain both hydronium and hydroxide. What defines a basic solution is that we end up with more hydroxide than hydronium. It's a seesaw relationship. What makes a solution acidic is we have more hydronium than hydroxide, which isn't the case here. And so this is going to be, go ahead and write out the hydronium, which is going to be 11 zeros and a 22. After the decimal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then a 2, 2. I'm going to carry extra digits, so I'm not allowed, but this is it. So this would be the inventory, what we'd expect to find in this solution. No, you can write it in scientific notation. It's fine. All right, any questions on that? Okay, we'll take a break. Then we'll start the lab portion. I'm going to talk a little bit about the lab. You don't have to. I'm behind in lecture, so you don't have to pre-lab this. So I'll talk about what we need for the lab. Normally, yes, but since I'm behind here. And that is, why was Ka for bicarbonate ignored?
Automatically supposed to be projecting on the screen.
Oh,
It's not
okay.
on.
Thanks. When we did our step 2, it was the bicarbonate hydrolyzing water, and it could hydrolyze in both ways. It could either accept a proton, like in this case, where it accepts a proton to form carbonic acid and hydroxide, or alternately, bicarbonate can donate a proton. If bicarbonate donates a proton, then it's going to form hydronium and carbonate. And the answer is this. We did Kb, but Ka here describes the same equilibrium as step 1. The only difference between this and step 1 is that step 1 defines the equilibrium in terms of pOH, whereas this describes it in terms of hydronium. And so we've already described there's a seesaw relationship between hydronium and hydroxide, and so it describes the same equilibrium as step 1. The equilibrium between carbonate and bicarbonate. This is the equilibrium here. And we're going to have a pH associated with that, versus in step 1, this is defined by the pOH. And so we have the same equilibrium, just defined in terms of pOH. And pH and pOH have to add up to 14. And so we don't have to do this. So this is why it's redundant to do it. It's already done. So we already have this equilibrium taken care of. We're just looking at it in terms of everything in terms of pOH. Okay. If we're doing acids, on the other hand, then of course we do the Ka and ignore the Kb. And the same kind of reasoning comes up for that. Okay. All right, so let's move on to today. We have an unknown acid, and so the first question comes up is, are unknown acids actually a solid acid? And this is carboxylic acids. Carboxylic acids are RCOOH, where R is just the rest of the molecule, or RC double bond O, and then an OH like this. This is the carboxylic. Now R can be quite big. especially in these organic acids. These R groups are, and they can have strong intermolecular forces, that is hydrogen bonding interactions, as well as London dispersion type forces. And so a lot of these organic acids are actually solids. The intermolecular forces are strong enough to hold the molecules together in a crystalline structure. Now the question comes up is this: our burette, our burette has a capacity of 50 milliliters. And when we do a titration, we don't want to just use a tiny bit. If we use just a tiny bit of base, then we have to worry about relative error. Like a 1 drop error in 1 milliliter is like 0.5% error. And so versus a 1 drop error in 50 milliliters is a very small percentage error. And so the more base we use, the less we have to worry about a 1 drop error. Did you overshoot it by a drop, undershoot it by a drop? It's going to become less significant. And so what we want is we want to use the maximum amount of base, which would be like 50 milliliters. But that's dangerous because if, let's say we needed more than 50 milliliters, then we'd have to refill the burette. Refilling the burette adds error again, because the more measurements you take, the more chance there is for error. And so the ideal amount is between, let's say, 35 and 45 milliliters we'd like to use. Give us some reserve. Now, in order to use 35 to 45 milliliters of base, how many grams of acid do you need to weigh out? It's an unknown acid, so we don't know. And so we'd have to do some trial and error. You just guess and then see how much it takes. And hopefully it works. But to avoid too much time wasted in trial and error, I think they give you a range. Do they give you a range about how much to use? Well, we'll take a look. Actually, let's take a look at the lab and see if they tell us how much base we need. Or how much acid. Oh, shoot. I thought I did these as individual. Maybe I didn't. Am I saving this? I don't know. All right, let's see in the procedure. Do they tell us how much base we need to, not base, I'm thinking the problem, acid, how much acid we need to use. Now everybody has a different acid, unknown acid. If everybody's acid is unknown, okay, it says use the analytical balance to weigh by difference. We don't need to weigh by difference. Weighing by difference is for old-fashioned balances. What we can do is we could just tear our piece of weighing paper and then weigh whatever we want. And so we don't have to do this weigh by difference. It's a waste of time. 0.1 gram sample. Do you think that's going to be the right amount for everybody? No. And so what we're going to do is we're going to do throwaway titration. The first titration we're going to use 0.1 grams and then see about how much we use and then adjust. Let's say 0.1 grams puts us in the target, 35 to 45 milliliters, then we're good. That's how much we need. But let's say 0.1 grams takes like 75 milliliters. If it takes 75 milliliters, that's such a hassle because you got to use 2 burettefuls. So you need to cut it down. Or let's say 0.1 gram sample goes to 20 milliliters. 20 milliliters is going to have a higher relative error than 35 to 45 milliliters. Closer to 45 is better. Or 40, to maybe target 40 milliliters. That could be good. Maybe just do that, target 40 milliliters. Makes the math easier to compute in your head. And so I double it. If 0.1's only taking 20 milliliters, I'm going to use 0.2. It takes me to 40 milliliters. And so what you're going to do is you're going to do a throwaway titration and then just use some proportions to figure out how many grams precisely you need to get 40 milliliters of titrant. That's the best. And you want to be as precise as possible, because the more precise you are on this, the smoother the real titration is going to go. The real titration is what we call a pH titration. It's very time consuming. And so what we're going to do is we're going to run some titrations with phenolphthalein first, just to get the optimum sample size. All right, so that's the goal of today's lab, is we need to determine the optimum sample size. And we're going to do a trial titration, maybe 2 trial or 3 trial titrations to figure what that optimum sample size is. Now you're going to check out the equipment, which is shown here. We're not going to use all the equipment today. We're just going to use the burette clamp and the Erlenmeyer probably. You could use the stirrer for practice if you'd like. We have a magnetic stirrer. Before, when you did this, you swirled it by hand, which is fine. Swirling by hand is convenient because you can wash off the inside from splatter. Sodium hydroxide splatters there, acid splatters there. We want to make sure everything's mixed. But in this case, we have this little Teflon coated magnet here, and we have something to spin it. And so you just adjust the RPMs. You don't want splatter, you just want a good mixing. That's it. And so we can practice with the magnetic stirrer. It's fine today. When you do clean this, don't dump the stirrer down the stir rod, we call it, down the sink. They're difficult to recover. Okay. All right, so that's the goal today. So then Thursday we're going to do the real titration, but we got to figure out what the optimum sample size. We're going to use phenolphthalein to hit the end point of the titration. All right, any questions on that? No? Okay, let's go ahead and check out the equipment. You could either do this solo or with a partner. It's fine.